grade, we had two sons. And one was a PhD.
My father, he used to do a gin mill, then he went into the butcher shop business, and he also wanted very sober around people working. He may have some stuff going on. And he's still around, 92 years old.
Memory changes lead to real clinical problems. We're not recognizing people that were with us for years. People are forgetting how to get to the times for years. People just aren't able to remember things that they used to be able to remember, to the point that it's affecting their life. And that's when they started to become more professional.
That's when Linda decided she needed some assistance.
People would come to the house and we just let them in. Strangers, perfect strangers, would let into the house. And they would stay for hours. And I was worried that they'd be walking around my house, checking it out later, or possibly taking things. Or I didn't know, he was signing contracts for services that we didn't need.
Now Linda takes Harvey to a special day center for Alzheimer's patients, where he spends time with his new friend William and a dozen other patients. Both men are living more stimulating lives as the day center helps them to adjust to their future.
That was one.
We'll slowly go through and start getting more and more.
I think this was the last slide.
Forgot one page over there.
Some of this is going to overlap before, but all right.
Everything's in your number 6.
There's some additional information here as well. One thing to keep track of to go through these things is hemispheric differences. And these are for someone that's right-handed. So there's some preference for right hemisphere to be more involved here than the left hemisphere. I might notice that here we have some regions here for looking at the emotional content or the affect associated various stimulus are coming in, either auditory stimuli or visual stimuli. Not surprisingly, they're associated with the respective areas. And things about the right hemisphere. We've already talked about the amygdala to some great extent, so we're not going to repeat that. Well, let's bring in also the forebrain, which not only allows you to have some controlled motor expression of whatever emotion you're feeling. But here's a little additional part that we actually can suppress. So just because you're feeling a certain response, feeling a certain emotional response to what you might be seeing does not mean that you're going to start, let's say, crying right out. You can control things. Remember, we've also talked about some detail. This is some of the parts we talked before. Remember the hippocampus, we talked about hippocampus, how it took short-term memories and turned into long-term memories. The major involvement of the limbic system in this, in the temporal lobe. So this is looking at parts we're talking for episodic memory, the different structures involved. Prefrontal cortex. This picture looks at some other ones, other types of memories. Again, we have talked about this before. If you're talking about procedural, we're talking about the cerebral cerebellum being involved in that. Learning tasks, motor tasks. This also brings back our basal ganglia here. Should be surprised. And here's supplementary motor cortex. So these are all work together in procedural memories. These are doing things, right? Semantic should be all temporal lobe. Notice that there's not really overlap between these different types of memory. And working memory is all prefrontal cortex. So different types of memory are involving different regions of the brain. Again, some distinction. Left hemisphere versus right hemisphere. Verbal language functions are mainly left hemisphere. Patterns tend to be more right hemisphere. So this again is episodic memory. It's just showing this is different slices of the brain levels. And looking at different regions which would be involved in episodic memory. I like this picture, it's an old one. It's actually asking for recall of, I think it was TV shows. This is electroconvulsive shock. If you look at more recent type memories, a big difference here. It looks more like it's more labile than some of the older memories. There's really no difference here in these older memories, but more recent memories are more susceptible to this electrical shock treatment. Tells you something about, it must be something different with more recent memories versus older memories. These declines basically the same way, right? We've had electrical shock treatment or not. The big difference is just for more recent. Okay, here's the second part. This is just looking at different ways of trying to figure out what's going on in the brain. We're trying to map out structure-function relationships. That's what we're trying to do, right? What part of the brain does this? Not surprisingly, exam questions are going to be like, what part of the brain does this? So here's some of the things, and basically you have two sort of different issues. Where and what. And unfortunately, we don't have good things they're going to be looking at both simultaneously. So you talk about structure, you get very good spatial qualities. You can have a very good, clear idea of what's happening. With function, sometimes with function, you can have very good temporal resolution. The temporal would be time-based. Trying to look at a function, it might make sense to be to have a good idea of things changing over time, right? Functions tend to change over time. So generally, you're splitting between doing one versus the other. So here's a CT scan. We have some of these now here. For dental, not for brain. So these are X-ray images, but they're basically added together by the computer to give you a more 3D type of picture. It's a static image. You've got basically a one-shot deal. It's not looking at, so function probably wouldn't work too well, right? Structure, not too bad. So here's nuclear magnetic resonance imaging. Actually, it has a better resolution as far as spatial. So I try to identify what you're looking at, has better resolution. Again, it's going to be a static image, right? No temporal resolution. Nothing really much about function. But you could tell if there is regions of the brain which are abnormal. Another thing you pick up with here is that you get white matter and gray matter, which isn't always possible. you're looking at X-ray, not to pick up some of this other tissue. Here's an example of this for diagnosis. This would be my image from a normal person. Here's an elderly patient who has normal cortical function. And here's a patient with Alzheimer's disease. The arrow is trying to show possibly differences in structural loss here you see in Alzheimer's patients versus someone who might be just as old as with normal cognitive function. So this is functional MRIs. Now we've got not only some idea of where we're looking at, and so it has some localization, not at cellular level, but it is a regional level, right? And this is functional because looking at oxygenation levels. So the idea is that if you have very active tissue, your oxygen levels locally should be your question, your easy question. More active, what do you think is going to be happening to oxygen levels there?
Question? Is there a question? Dude, my freaking computer won't work.
Okay, so increased oxygen. You're probably extracting more oxygen from the blood, right? So this would be which lobe? My 4 lobes. This lobe here, what do you think? The occipital lobe, right? So looking at this picture, see anybody else see something lighting up here? What about this? How about if we do 4 lobes here? We got to do 4 lobes. You said this wasn't working here. Is it working? Okay, 4 lobes. Let's say frontal, parietal, temporal, occipital. Right here. Did it light up? Paying attention to this design here in the visual field. Most of what we see is in the occipital lobe, primary visual cortex. We see something up here. Which lobe do you think? And it fits in with the name of what we're actually looking at too. The answer should be all over the place, right? Okay. So I said you were paying attention. That was so clear. That was what I'm trying to get you to think about. So if you're trying to look at something, where do we have activity? It's a very specific name. Frontal eyeball fields, right? We talked about this before. So not only, if you're not paying attention, not looking at something, it's a little hard to see it, right? Something has to direct your eyes over there, which means it's motor, frontal. Okay, so now we're getting functional and anatomical. So now we know that this region's being activated. There's some other regions being activated. We're looking at this pattern. This is positron emission tomography. In this case, we're giving glucose, which is tagged. So we're going to look for the tag. And this isotope actually gets concentrated where glucose metabolism is highest, which means they have high activity, right? So a bit of a dynamic picture now. So we still have some spatial resolution. Temporal resolution isn't too good, but you could probably see that, oh, decreased activity here and the structure. Should be a problem. What structure is we're seeing the decreased activity in? Substantia nigra, most likely, right? Decrease in substantia nigra associated with Parkinson's, that makes some sense. Same technique, so the areas that are lighting up are of higher activity, more glucose utilization. Remember, the brain uses glucose for all its metabolism. So, talk about language task. So you expect temporal lobe is involved. Temporal lobe is involved here. There's some frontal lobe involved as well. But it depends on whether you've actually practiced doing language tasks or haven't practiced before. And there's different types of areas that light up depending upon. Don't memorize areas, but say that depending upon, it could be the same task, but if you've done it before, it involves different parts of the brain than if you've never done it before. This is spectrophotometry. This is looking at blood flow. Again, blood flow should be highest where activity is highest, right? I have some problems with looking at spatial here, but it could measure changes in blood flow on a dynamic scale, right? Spatial, I have trouble finding out the structures based upon this kind of picture, right? I do, I don't think you guys. So one of the ideas is to do an MRI, which gives you very, very nice detailed structure. Overlay the two, and you can actually bring this out. So what do you think would have the best temporal resolution? Not just from these two. All the different types of things we're talking about. Temporal. Give me a hand.
Yeah.
The whole lecture. AEG, right? What was the spatial resolution for EEG? Really lousy, right? We're basically talking about whole lobes, perhaps, with electrodes in place. I just want to mention what cognitive subtraction is. What you're trying to do, look at a function of some structure or some task, to try to figure out where the function is going on. What you need to do is have two tasks that are very, very similar. So they do one task, you do the measurement, say spectrophotometry, and then you do the reading for that, and then you do the task which only differs in one part, the one you were actually interested in. And then you subtract your activity or your blood flow from one versus the other to see the difference. So it's like subtraction, right? Here's your control, here's your function you're trying to look at. And the two things should be very, very close together as far as what you're actually doing. So you don't want to have all the other things that go on in the brain associated with any type of function. You're not interested. You're only interested in very specific tasks. Here's another one. This is an evoked potential. So this is not like an EEG, though it's an electrical recording. So this is in response to some stimulus, which we didn't see with the EEG, right? EEG is basically the overall activity of the cortex. This is a response to specific types of different stimuli. This one was just showing that spaces get dealt with differently than other types of objects. Spaces. Okay.
It's just like one.
Next part.
And you like missing words. It's just not described.
This first picture just shows that left and right hemispheres are not identical anatomically. There are some differences. So we can see the sylvian fissure is different on the two sides. This cross section, this seems to be in a bigger dimension than on the right side. And this picture, this region, is much bigger on the left than on the right. So this portion of the cortex is the one that's involved mainly with language skills. So not surprising if all your language skills are on the left hemisphere, it makes some sense that you have more region of the brain devoted to language tasks, and then you have a larger portion of that on the left hemisphere than you would have in the right hemisphere. Since the right hemisphere really doesn't have a language function. So that sort of makes sense, right? Well, we also see these kind of differences in primates, which really don't have a whole lot of language function. So, hopefully in anatomy you learned this already. The way the visual fields work out. Gone through that? Remember that? So the way the optic nerves transverse back from the retina means that information from a visual field is processed on the opposite cortex. So the right visual field, which is information hitting both eyes, is processed over on the left hemisphere and vice versa. So this picture of the bird, even though the information goes to both eyes, this information goes straight back to the left hemisphere. And this information crosses over the optic chiasm and again gets processed in the occipital lobe of the left hemisphere. So remember that. That's going to be important to keep track of. Remember the different sensations were basically going to be contralateral, right? So was it exception? Somebody was in my office this morning, should remember what the exception was? Which one was it? Exception? Sensory. Input.
Primary taste? Primary taste?
Taste, right? Taste wasn't. Taste is the only one telling switch over to the opposite side for sensory input. Motor output goes the opposite side too, right? Language is going to be all left hemisphere. Some of the other things go over to the right hemisphere. We're going to look at this in more detail. So the first step is to look at studies probably done with undergraduate students. We're trying to look at which hemisphere is doing which types of functions. So the basic setup is that the subject fixates, so they're looking straight ahead at the dot, basically. And then you can present information to one visual field or the other visual field. These are done very rapidly, so they're not up there long enough, so you can't cheat and shift your gaze over to the other picture. And then you can ask them to visually answer them, or they could use some type of manual, using their hands, for example. Then you see whether people can do these things rather rapidly, and you can also look at accuracy. So that's the general setup. Here's the 4 levels of difficulty. You see something or not? Pretty easy thing to say, right? What? If you have 2 simultaneous stimuli, you have to figure out whether the 2 are the same or they're different. That's your choice of answers, same or different. That's easier to do if you actually had successive. So the picture here, then a few seconds later you show a different picture, you get the same one. It's a harder task than if you have 2 pictures simultaneously to 2 different visual fields. And finally, the identification, what you're actually looking at, takes longer. It's a harder decision to make. So I'd say these are probably pretty easy discriminations. Everything's different. And these are a little bit harder type of discrimination. It seems that the left hemisphere is just a little faster at these easy discriminations. So it picks out these a little faster than the right hemisphere. This would be relative.
It's embarrassing to you.
Speed and accuracy. I like this. It's called the holistic bugs test. And it depends upon what kind of question you're asking. If you're asking a question about are all the different parts of the bug the same size, that's more of a holistic type pattern. Right hemisphere seems to be a little bit faster at that type of decision. If you ask, what is this? I can't remember parts of the bug. Abdomen? I don't know. What is that? Thorax? I don't know. What is it? Thorax? Okay. I haven't done bugs in a long time. Thorax, if it's spiky or not, that would be a specific detail, and the left hemisphere does better on details. So details versus patterns, holistic patterns. That's a good discrimination. So here again, if it's a face, it's a feature analysis. Are the eyes triangular or square type of thing? That's the left hemisphere type of discrimination. If you're talking about actually recognizing a face or emotion on a face, that's the right hemisphere function. So doing it with normal subjects is difficult because the information can rather easily flow from one hemisphere to the other. So a lot of studies were done with serotomy patients. Again, here's just sort of basic view of the picture. So they're showing 2 different pictures presented to respective visual fields. So the cat goes to the left hemisphere. The left hemisphere is the one that can talk, right? The one that has language. So here's our commissures. So the main one we're talking about is the corpus callosum. This is all axon, called white matter. That's all the connections going from cortex to cortex. It's cortical connections. It's the major one. It's fairly thick with all these different axons. It's just axons crossing from one cortex to the other. There are 2 other commissures too. So remember about the the visual field, I keep track of that. Then we figure out what happens if we actually disconnect the hemisphere. See if this will work. Just found this one this morning. Switch on.
Everything we human beings ever do, no matter how ordinary.
This one. Why is my whole one open?
I was like, actually, you're kidding me right now.
That's a little loud.
We began our journey into the human brain here on the campus of Dartmouth College in New Hampshire. I'd come to meet one of the world's leading brain scientists, Mike Gazzaniga, and a man he's worked with for over a decade. A man with two brains. You've been working a long time with Dr. Gazzaniga?
14 or 15 years.
It doesn't seem like that, does it?
The collaboration began when Joe had surgery. And you had this procedure to correct an epileptic problem, is that right?
Trying to stop the seizures. I was having seizures like every day or so, or sometimes 2 or 3 a day.
To control Joe's epileptic seizures, a surgeon severed the connection between the two halves of his brain. Cutting the corpus callosum like this prevented the spread of the electric storms that caused his seizures. But it also prevented the left and right halves of his brain from communicating with each other. In the years since the operation, Joe's epilepsy has been under control. He now earns a living at an egg farm, and in his everyday life, he's largely unaffected by the fact that his left and his right brains work independently. Do you feel any different when you think about something than you did any differently from the way you felt before the procedure?
It's a backup brain, that's all.
That's something everybody could use. I found out how true that was right away when I was asked to draw a different shape with each hand. In a brain like mine, roughly speaking normal, at least all in one piece, the left half of my brain controls the right side of my body, while the right brain controls the left side. Oh, no. But because the two halves are connected, nothing wrong with that. Getting each hand to work independently isn't easy.
Well, we're seeing the fact that Alan's hemispheres are connected, and that the motor messages from one are confusing the motor messages in the other.
I was just drawing an upside-down duck. Okay. But when Joe is given the same task, his two hands operate as if controlled by two separate brains. What's happening is that each half of Joe's brain is given a separate instruction. He's asked to fix his eyes on the cross in the center of the screen. Anything flashed to the right of the cross goes only to his left hemisphere. Things to the left go to his right hemisphere. Because the two don't communicate, each hand does only what its half of the brain sees. Wow. It's really like two different people doing the same.
That's right.
Same task.
That's the idea. Okay, Joe, I want you to keep your hands out in front.
In an experiment that's now a classic in brain research, Mike Gazzaniga over 30 years ago used a similar setup to find out if the two halves of the brain are specialized to do different things.
Sure.
Joe is being flashed a word only to one half of his brain. Words flashed to the right
Storm.
are seen only by his left brain, and Joe can report seeing those words just fine.
Piano. Good.
But when a word is flashed to his right brain,
Didn't see that.
Okay. So I'm going to ask you
but now watch what happens.
to draw that with your left hand.
I think I'm lost.
Why don't you try drawing another picture of it over here, if that'll help you.
All full.
Oh, okay.
Sure.
It's almost as though somebody has given him a secret communication.
That's right.
Now he knows that it's a telephone. Up until then, he was blind.
Exactly.
When Gazzaniga first did this experiment, it instantly proved that the ability to speak resides almost exclusively in the left hemisphere. Not until he sees what his right brain is drawing is Joe able to name it.
He said church, after looking at the picture.
But he had to figure it out about as long as we did. That's really interesting. It's a picture here of somebody communicating almost with another person.
Communication is not occurring inside the head, it's occurring out on the piece of paper.
Yeah.
Bob. I don't know.
Draw a little bit more.
So far, Joe has been seeing only one word. Things get even stranger when he's flashed two words, each to only one half of his brain.
The right hemisphere saw toad.
Yeah. And so his left hand draws a toad.
There's the toad.
Oh, it's a toad. Right. This time I was able to guess what was coming.
Now put a little three-legged stool in there.
Joe's speaking left brain saw a stool. Saying the word lets the hand that's controlled by his right brain in on the secret. That's great. That's really interesting. And if he had seen that with the corpus callosum intact, he would have drawn a toadstool.
Right.
Not a toad and a stool.
Right, exactly the point. I've been doing this for 35 years. Yeah. And it gets me every time.
Yeah.
Time instead of naming the word, I want you to point to the word.
Again, Joe sees two words simultaneously. Bell goes to his non-speaking right brain. Music to his speaking left brain. When asked to point to a picture of what he saw, he chooses Bell. But when asked why,
Okay, why'd you pick that one?
Music.
Music?
and when asked to explain,
Was music and bell, and it was a few minutes ago, last time I heard any music was coming from the bells out here, banging away.
So the bell's outside here.
So, we're putting up answer to me.
what's extraordinary is that Joe's speaking left brain concocts a plausible story of why he pointed to Bell, even when some of the other pictures more obviously represent music. Gazzaniga believes this determination to find cause and effect, this desire to explain, is the left hemisphere's most marvelous property.
One of the unique things of the human brain is this need to interpret why two events occurred. What was the antecedent of this? What caused this? And if you can imagine that a species like us that has that little chip in its brain that asks those questions is going to survive rather well, because it's going to figure out more about the nature of the world than a species that doesn't have it.
Okay, Joe, I want you to keep your hand.
But as I was about to discover, the right brain has a very useful survival skill all its own. What do you think will happen here?
For you, we're doing a live experiment. Never done it before.
The experiment involves the 16th century Italian painter Arcimboldo, who made faces out of fruit, flowers, meat, even books. From other research, there's reason to believe that the ability to recognize faces is located exclusively in the right hemisphere. So Mike wondered if Arcimboldo's paintings would look different to each of Joe's two brains.
So will his left hemisphere say, I saw a potato, I didn't see a face? And will his right hemisphere say, I saw a face, and unconscious?
So that in psychology. That's not in psychology. Of course, leave it to Regan to take the fun out of it.
Exam question.
Leave it to Regan to take out the fun out of things.
Ouch.
So, when you split that, you are not allowed to communicate anymore. So again, we look at relative functionary differences between left hemisphere and right hemisphere. So again, remember how things can project possibly might be exam questions. This is another one I thought was interesting. So this fits back to what we just saw as well, is that two hemispheres work differently. So this was the picture, similar to what they showed there. This one's going to the right hemisphere, this going to the left hemisphere. So this hand picks out what is seen in the, which visual field is this hand going to pick up?
On the right.
Supposed to pick up the right.
Okay, this hand, which is the left hand, will pick up, it's associated with which visual field, right or left? The answer is,
Right. You said right or left? The left.
okay, so this picture goes to the right hemisphere. The right hemisphere controls the hand, okay?
Yeah.
So the hand and the visual field go together, right? Both are primary contralateral. Now remember, there's only one hemisphere that can talk, right? The hands are going to be controlled by the respective hemispheres. Only one hemisphere can talk. So if you ask the patient, why did the left hand pick up the shovel? And that hemisphere which can talk only saw whatever, chicken foot or whatever. What do you think they said?
Pick up chicken.
Basically, it was for shoveling up the stuff after the chicken ate it.
Wait, so if you ask the right brain why the left hand picked?
Well, the only one that can talk is the left hemisphere, right?
Okay.
The left hemisphere saw. What the left hemisphere, what the verbal hemisphere saw the chicken foot. So the shovel was clean up after the chicken. So just like you brought up, you made up that whole connection between music, and that's what the bell tower was, which really wasn't a very good correlation at all. So his left hemisphere is actually able to make up the story.
Why wouldn't he? His other hand's pointing to a bird. Why would
That makes sense because this is, you get here, this controls the hand, right? Check goes with the foot, right?
I thought you were saying that the shovel goes with it.
No, but if you ask why the left hand picked the shovel,
Oh.
the left hemisphere doesn't see the snow, right? So there's the idea that the left hemisphere can actually anticipate. There was some idea that maybe when people have these false memories, is that the left hemisphere can actually be very inventive, come up with explanations that weren't really true. The left hemisphere came up with them by themselves.